Okay, thank you to be here for the lecture of today. Let me reconsider very shortly some aspect of the last lecture. Then we will do some exam exercises. We have a transformation T from V domain to W codomain in a linear transformation LT. Now, concerning the surjectivity. Sometimes in some books, the subjectivity is indicated with the word onto, huh? But subjectivity is more used. If for every element W of the codomain, we are speaking about the codomain, W not capitalized, capitalized is exactly the set. There exists at least an element V, not capitalized, which belongs to the domain, of course, with which T of V, not capitalized, equal W. Very important for every element. This means, you remember last time, I have to cover every element. This means I have to cover the whole codomain. In fact, if you remember, let me see if I find quickly the scheme, probably yes, I hope. You remember the graphical scheme? No, it's not here. Otherwise, I can redo them, but should be better if I find quickly. So, yeah, probably. No, it's not here. Okay, I will do. In any case, if you remember, this means exactly that if it's not surjective, that the codomain is not totally covered. And remember x squared. X to x squared, the function x up to 2, is not surjective because I don't cover totally the codomain R. I cover just R plus. This means the positive part. There is a nice scheme which I put last time, which I am not able to find, but I can check again a little bit. Yeah, otherwise I do it. Let me switch on the lateral camera. Is the domain V, and here's the codomain W. W1, W2, W3, and so on. For instance, V2 not necessarily in W2, could be also here. This transformation here is not surjective, because I don't cover, let me say a little bit abstract the definition, but the whole element of the whole codomain. The transformation is not surjective. Is injective? Yes, because we have just how possible to for each element of the domain you have just one. Not better to say. Let me verify better here. The transformation. Now you clarify better. No? Is injective. The reason is for different, let me apply the definition. For different element of the codomain, the domain, we have a different element of the codomain. This is, I would like to say, yeah, the best. We have, do you remember, we have a couple of definitions, but this is the definition which I like. No? Different element of the domain implies different element of the codomain. What about a not injective? Something like that. This is not injective, not surjective. If I have in the exam, please graph and transformation and a surjective and injective transformation, and we are able to do any possible combination in the context of these possible questions. I think, again, if I have a V3 here, a V3 cover V2, excuse me, V3 cover W2, we have a transformation function, you can say also function, which is surjective and injective. Now, let me go ahead scrolling this a little bit the slide, and then we will do something related to the matrix. Look at this remark. Could help in some kind of exercise. A linear transformation T from V to W is surjective if the dimension of the range means probably it's better to use the word image because it's the same. Image, it's easy to remember. I'll show you why. Equals the dimension of its codomain. If you think about the picture which or the graph, we can understand well. Because as I told you, surjective means that the whole codomain is covered. We can see here the image or range is in a set characterized by W1 and W3. Basically, the image is intuitive to remember, because if you think of the transformation as a projection, this element V1 and V2 are projected in W1 and W2, and W1 and W2 is the image of the transformation. If you want, they are the image of V1 and V2. In this case, the transformation involves just the V1 and V2. It's defined in V capitalized, but you use just two elements is present. Of course, in the function which we have seen in math, we have seen continuous domain, dense domain. This means, you remember, R to R, here it's just to fix the idea. Of course, this is a transformation in which we have elements from elements of V to elements of W. Nevertheless, in a transformation. Very often, practically, is more used this in some fields than the mathematical function. The function is also a transformation. And a line is an injective and surjective. Do you remember? X squared is injective but not surjective, because not cover all possible elements of the codomain. Exactly here. This means the image, roughly speaking, if the image is not equal, let me say, of the domain, of the codomain, excuse me, exactly, yeah, the image is not the codomain. You have a difference. Because correct, V2 is not in the image. This means we are not speaking about in the surjective transformation or the transform. Therefore, it is written here. Yeah, this sentence here in form of dimensions or dimension, because we are speaking about transformation is more than let me say one dimension. Do you remember R2 to R3, R3 to R2, R2 to R2? No? This means it makes sense to define or to think about in terms of dimension. But what I told you before, that the image does not cover, very important. The codomain is probably more general, because of course, if they don't have the same dimension, they have the difference between. Exactly. Yeah, about the notation, I don't want to spend energy. Look at this theorem. If a linear transformation is surjective, this means I cover the element of the codomain, as I told you now, then the dimension of V larger or equal the dimension W. I think we can do some example in order to understand. What do you think? This theorem here can a little bit help. Or let me a little bit go ahead, then we will reconsider later. This is easy, no? Say that a linear transformation is invertible. Invertible means I can build a correspondence between codomain and domain if and only if is injective and surjective, both. Let me fix here the idea. Is this invertible? Excuse me. Is this invertible? No, because this element doesn't have a correspondence. Let me say in this sense in V. You remember, and a function is and a function is in a transformation, but a transformation is a transformation in the strict sense if each element of the domain have a correspondence in the codomain. This means from VW is in a function. Because each element and one and only one, please, I forgot to say, element in the corresponding element in the codomain. But if I consider a possible inverted function, it's not a function, something from W and V, because this element here doesn't have any correspondence, because each element must be one and only one. From here to here isn't a function, but from here to here, we don't have any correspondence from this one. But it's not a big problem if the transformation is not surjective, because we can consider just the image. We can restrict the image, and then we can say that in the context of the image is invertible. We can don't consider this one. Look at this. Here is the same. Here's the same, but the same, I mean, is not surjective. But if I don't consider this, also the image is not invertible, because from W to V, we don't have any function, because to W1 we don't have just an element. We have two elements. This I told you. Let me see one which is invertible. And so on. I can put also Vn element. We can see here this is easy to see. But of course, also in this case, again, the function or the transformation is not injective, or if you consider here, is not injective related to the image. This means even though I consider the image, I cannot invert because the possible inversion is not a function because we have two elements instead of one. Each element of a domain should be just one corresponding element in the codomain, just one. This means if it's not injective, in this sense, it's not a function. This means it's not invertible. Do you remember this? A linear transformation is injective if and only if the kernel is a trivial one, dimension of the kernel equals 0. Just the zero is in the kernel. Do you remember? Yet it was in LaTeX error. I hope to find the right lecture. This is now corrected. Yeah. And a matrix consists of m row and n column in this notation here. What is the rank? Very important. The rank of a matrix is the maximal independent number of columns of rows. Very important to remember, but it's not so difficult. Now we do exercise. In the common notation, we speak about rank of row, rank row, and rank of column, excuse me, row rank or column rank in case of rank of column. Very important this. In a full rank matrix with m row, I would like to say here, it's not exactly correct. I would like to say in any matrix with m row and n column, the rank of row equals the rank of column for any matrices. This always. Here I have to cancel full. I don't know why it is. Yeah, this was corrected. A number m is the number of independent row, is the dimension of the image. I show you this exactly now. And the total number of row is the dimension of the codomain. We can see the difference now. We can see the difference because not necessarily all row are independent. We can see the difference. No, everything's correct here. N is always the number of the column, the dimension of the domain. I think, let me tell you about these two slides, and then we will do it exactly. The nullity theorem, I think you remember. The nullity theorem you remember. We have this theorem here, which says the dimension of the, let me start from here. This is better. The dimension of the domain, this means the number of columns of a matrix will represent the transformation. Again, we have a perfect correspondence between transformation matrix. Equal what? The dimension of the image, very important, the dimension of the image, which is not necessarily equals the dimension of the codomain, plus the dimension of the kernel. This means the transformation transform the elements in the image, as I told, as you remember, as I showed you with this easy graphical representation, and the rest, if we have an rest, in the kernel, because the transformation somehow maintain, how possible to say, everything which transformed, we don't lose. This is a little bit something reflects the conservation of the information. What I have in the domain where I transform will transform in the image, or, and if you like, in the kernel. We can see here the dimension of the kernel, dimension of n, equals the number of columns, because the dimension of the domain, minus the rank of the matrix. This means if it's in a matrix and rank k equal n, we have the dimension of the kernel equals 0. This means it's injective. Remember this. Exactly what I told you here. We can see here. The theorem works in both directions. If the kernel is just element 0 is injective, the kernel is 0. This means the matrix at rank equal k. Yeah, the last thing, then we do exam exercise. In this sense, now we can conclude many things in accordance with this preamble. This means if the rank of the matrix is the highest, the max, it can be full rank, then it is injective, if and only if, look, the number of the columns less or equal the number of the row. Viceversa, is surjective if, now we do some exercise, if and only if the dimension of the number of the row larger or less than the number, the number of the column, and larger or less the number of the row. Okay, let me do some exercise, then we can understand better. Let's consider matrix. The matrix, as I told you, represented a transformation. Look, we have n equal to 2 column. We have m equal 3. 3 rows. Think 1 second, and then I will give you the answer. But this question here is the corresponding injective. And then we will look at other questions. Think 1 minute and then I will answer you. We have a dimension 2, which is transformed in dimension 3, from a small dimension to a large dimension. M is the number of the columns, no? It's not. Answer. Now we discuss. It's not injected. Now, the reason is the directly using the theorem which I told you, or the properties, that the number, why that? N, yeah, in this case, one second, probably I made mistakes, or yeah, it's the contrary, you know, it's the transformation is injected, excuse me. Now we clarify. Because n is less than n. This is I told you until now. Now, this means how I can demonstrate mathematically if this basically is injective. If you don't believe this theorem here, even though yeah, where I can, how I can justify this practically. Because we are moving from let me say, from a small domain to a large domain, as if I expected that the null is not consistent, it's just the kernel in the sense, it's just the zero element. It's clear, it's a little bit intuitive, but let me analytically demonstrate. I mean, if you remember this theorem here, you know already the results, as I told you last time. Let me calculate the kernel of A. Because basically, analytically, until now, we have seen that this can be demonstrated using this here, this calculation here. Basically, I would like to test if the kernel is the set of the domain at dimension 2, and the codomain at dimension 3. Let me write this properly. It can help intuitively also. The domain has dimension 2, and the codomain has dimension 3. Let me look at this. x plus y equals 0, y equals 0. This means I don't need to go ahead, but anyway, if you want, I can write also the last equation, but we can see directly from here that x equals 0, y equals 0, which satisfies also this one. As I told you, just 0, 0 belong to the kernel of A. This guarantees that not injective. Injective, I made already mistake. Yeah, it's injective. This means exactly what I told you before. Intuitively, if we have the number of row, the column, less or equal the number of row, not, I don't speak about independent row. We have the injectivity. I don't know, let me see again where I told you this one. To avoid mistakes, as you have seen also, I made mistakes. Try eventually. I mean, in the question, I will pretend that you calculate also the kernel. This means the kernel is exactly everything which we need to. It's here to demonstrate. I don't know if it's easy to remember, probably not extremely easy, but think about that. We expand, let me say, the dimension. Better to say the transformation expand the dimension. This was from R2 to R3. Is surjective if and only if the number of the column larger or equal the number of the row. Okay. Let me see if I can. Yeah, also from here. No? But I think the test is this one. Let me look back if I can add something on this topic here. Okay, let me see in a subjective case now. Okay. Subjective case probably a little bit more interesting. Okay, probably, let me see, let me conclude here. In your opinion, we have seen that is injective. Is this transformation subjective? When the transformation is subjective? I think we have seen in different form. But if you remember exactly what I told you when I started the lecture of today, this means the dimension. Today I told you intuitively when the image of the transformation equals the codomain, just roughly, no? Just roughly. More mathematically, no? You remember I told you the dimension of the image equal the dimension of the codomain. It's equivalent to say the cover, the whole codomain. This means in this technical context, this means that the number of row must be equal the number of independent row. But if you remember here, what is the maximal rank of the matrix. The maximal rank of the matrix is 2. But if you remember the theorem that the rank column equal rank row, we can see directly that the maximal rank row is 2. This means it's clear we have 2 independent columns. If you want, I can do also the calculation we have seen last time. No? Last time we have seen the calculation. It's the exercise which I did related to the independence of columns. But in any case, it's clear to see for different reasons. I clarify how we can intuitively look at the independence of elements of vectors. It's clear this 0 here, this 0 here, definitively says to us that the 2 columns are independent. Now, the rank, the maximal rank, the highest rank is 2. This means the row, they are depending. This means it's not subjective. You know, so if you want, I can try it before doing this. Let me write. Matrix A does not represent a surjective transformation. Well, in fact, the rank, the row rank, equals to no full, if you want to use some notation, which I introduced, and no full rank. This implies, in order to understand it a bit better, that the dimension of the image of the transformation, clear, is not equal to the dimension of the codomain. Dimension of the image not equal to the dimension of the codomain. Now, the other exercise, another exercise. Your opinion, is this injective or not? Now we have seen the trick. No? This was injective. I mean, it's not the same matrix, but we can see that we have let me say, roughly speaking, a vertical matrix. You remember last time I told you also as a possible trick to have an advanced answer. This was injective, you remember? Now we have, in this case, the matrix with more row than columns. Here we have a matrix with more columns than row. This means this one cannot be injective. About the surjectivity, we have to be careful because we have to demonstrate that the 2 rows are independent, because in the surjectivity plays a role the difference between the independent and not independent role. This is a little bit the concept which we have to consider. Why it is not injective? It's not injective because this 3 column in a matrix with highest rank equal 2, the highest rank is 2. 1, 2, more than 2 cannot be. This means one of these 2 columns, at least one of these 2 columns, depended from the other 2. This means it's not full column rank. This is enough to say that we have something which is going to 0. Something means in a dimension, at least, that it is going to 0 in the kernel. If you intuitively think, as I told you, I tried to do before, here we compress somehow, compress the information. I would like to say the information. Here, do you remember I told you just roughly, just to figure out. Here we expand the information from R2 to R3, or at least we try. Here we compress from R2 to for R3 to R2. This is intuitively. Intuitive. Let me do analytically. Analytically, again, the kernel, at least until now, we have seen that this thing can be analytically excuse me, here also I made a mistake before. Okay. What I'm doing. Yeah, I would like to correct. I calculated correctly both three, but the dimension. Excuse me for the. Yeah. Yeah, I did correctly, but here I forgot to do 1 plus 1x plus 1 epsilon equals 0, epsilon equals 0, or y equals 0, 1 x plus y equals 0. Here I did correctly, but I forgot to put here. Is here now the dimension. Excuse me for that. This means x equals 0, and here we have x plus y plus z equals 0. I transform a set of the domain into 0, 0, but the dimension of 0, 0 is exactly the same dimension of the codomain because it transforms into 0, 0, but is the dimension of this 0, let me say so, is the dimension of the codomain. Otherwise, I cannot write consistently this equation. Here I did correctly with 3 dimension of the 0, but I forgot. Okay. This means if I plug in here, we have I can write y equals minus z. We can see that the dimension of the element 0, excuse me, of the kernel is not 0. Zero, because is written here. And then I can consider this, or if equivalently, as you like, you can consider this for this. What do you want? This one. I don't know if you agree, for each z. Y and this position equal minus z, but for each z. Let me write here correctly. See, everything's correct, but in order to understand better, this I can write minus z for each z. Or y equal minus, z equals minus y for each y. Equivalently, in the same way, kernel of A equal, the only A is no, 0, because I have to fix this. But now we can see, I can write everything is in the function of y. Z equals minus y, and here y for each y. I don't know if it's difficult to follow me. No? One of both. But it's clear that this vector here for each y is transformed into 0. This vector here for each z, this means is in a direction, this direction, or this direction. But it's the same direction. It seems to be different, but it's the same. Because if I multiply the same in the sense they are two parallel vectors, but two parallel vectors indicate the same direction. You remember at the beginning of the course. If you don't believe me, try to put here. 0 multiplied this, excuse me, this row multiplied this row is 0. 1 multiplied 0 is 0. Plus 0 multiply minus 1, plus 0 multiplies 1. This is clear to see. If you do this row multiply this, we have 1 multiply 0 is 0, and then we have 1 multiply minus 1 is minus 1, 1 multiply 1 is 1, but I have to consider minus 1 plus 1, it is 0 nevertheless for each set. Here can be also, we can do also the same. Okay, let me think if I can a little bit more in depth. This is more or less what I can ask on this topic, on this chapter. Yeah, let me consider another kind of exercise. We are here to do exercise, no exam exercise, because it seems to me that this semester, as I told you, not all semester I propose the differential equation. It depends of the students, depends of, but if you want to hear, let me say so, something about the differential equation, you can eventually ask if it is possible to attend in any case, but to consider for your examination as an yeah, optional course, this course in dynamical systems. Let me now consider let me see. I found. I think this we didn't do. Yeah, I think this, I don't remember. Or let me go a little bit ahead. Could be that that's a little bit. Okay, this is nice. Let me consider this. I think I didn't tell you about this two exercise. I don't think so. Okay, 1 second. Look at this. I have a linear transformation from T R up to 2 to R. And I give you this data. The point of the vector 2, 1 is transformed into 2. The point of the vector 1, 4 is transformed into 2. No. If I ask directly, is this injective or not? Think 10 seconds. It's clear that it's not injective. Why that? Because from the information which I gave you, we have two different elements by do you remember elements in this case is vectors, two vectors. We have in this case the vector v1 and the vector v2. Here I sketched quite generally with two elements, but in our case, what is element or elements are vectors v1 and v2 concretely 2, 1 and 1, 4, but both are mapped in the same value. It's exactly the situation here. At least in the context of the injectivity. About the subjectivity, we will speak later. But it's clear, no? We have two different elements mapped in the same element, in 2. This means directly I can say that the transform is not injective. Let me demonstrate, justify. Yeah, here's a little bit. Yeah, but then it's clear the question. No? This is an exam question. Justify the answer. If I write justify, the answer is not clear because I can justify graphical. What I intend to do. Nevertheless, in a justification, if you justify graphically, but I am asking you justify the answer calculating the kernel of T. Look. In order to calculate the kernel of T, very important now, in order to calculate the kernel of T, I have to construct a transformation. This means I have to calculate A and B. I mean, look at this sentence here, we formalize the transformation from R2 to R. Each element of X and Y, in accordance with the transformation, X comma Y, R2, this is belong to R2. All these elements, or these elements, X and Y, basically each element of R2, if you want, which is characterized by X and Y. Each element of R2 is transformed. Each element of X, Y of R2 is transformed of A multiply X plus B multiply Y. Because do you remember, it's a linear transformation. Linear transformation, as I told you, a linear combination of element of X and Y. This means is the sum of X and Y, but multiplied by two constants. The goal of the exercise is to calculate A and B. Is again, I wrote for you because this is an indication which I will give you in the exam. Now, how I can build this system here? It's not so difficult because if you look at the data, if you look at the map, we have X equal to and Y equal 1. Here. X equal to and Y equal to 1. Mapped into 2. This means A multiply 2 or 2 multiply A because X is equal to plus 1 multiply Y, excuse me, B multiply Y because Y is equal to 1, as I told you before. Maybe it's easy to write and to explain, but in any case, X is equal to, this means in accordance to is 2, no? In accordance to this expression, we have a 2X, excuse me, 2A plus 1 multiply b. Why that? Because y is equal 1, and I have to multiply by b in accordance with what I wrote before. Mapped into 2 because it's written. Look at this transformation here. This transformation here. In accordance with this general transformation, we have a plus 4b equal 2 is clear, because it's written here. But why a plus 4b? Because x is equal 1. This means 1 multiply a. Y is equal 4. This means 4 multiply b. Everything is equal to. Now, if you try to calculate the solution in accordance with what we learned into in the gymnasium, no? Believe me, that is easy to do. I calculate explicitly b. B is 2 minus 2a, and then I plug in b here, and we will see now this expression. If I put b here, I do some boring calculations. It's a shame we have to do also this one, and we can see that we have this calculation here because we have a plus 8 minus 8a. This means minus 7, 8 plus a equal to a equals 6 divided 7. If a equals 6 divided 7, I plug in here, and we'll have the results b equal 2 divided 7. Now I have the transformation because if you reread the example, the example says calculate the kernel. Judge if the transformation is injective or not. Before I forgot to say something. No. I think I told you everything. It's okay. Remember, if we discussed the surjectivity of this, probably yes. We discussed the injectivity. It's not, no? Because it's not zero. It's never very subjective. No? I don't remember if we discussed. It's subjective, yes, because we have two independent rows. It's easy to see. Last time, I did exactly the demonstration that this row, this vector, the row vector, is independent with this one. We will see later another exercise. Probably I forgot to complete. But anyway, it's okay. Now we have a transformation. This is A, this is B. Now we calculate the kernel, and with the kernel we can judge if this transformation is injective or not. Easy to see that the kernel is not 0, 0. It's minus 3x, y minus 3x. We are in a direction which is transformed into 0. For each x, we can express in this form here. As I told you before, we have x and y, the set in the domain, which is R2, which is transformed into 0, 0. Into 0, excuse me, into 0, because the transformation is R up to 2 to R. It's easy to write and to explain. 1 minus 3, because y is minus 3x. X is the parameter for each x. This means the dimension of kernel is equal to 1. It's not injecting. Now, in your opinion, is the transformed this here, the transformed this here, subjective? Think 1 second. Concentrate. This means here, the matrix is 6, 7, 2, 6 over 7, 6, and 2, 7. I reformulate here the question. In case I question you. Yeah, let me do. this transformation can be written in terms of matrix A, this form, right? In your opinion, is this transformation surjective? It is. Why that? Because the maximal rank is 1. It's not injective because it's not full column rank, but it's full row rank. Because this matrix here, the highest rank is 1, which is the row rank. It's exactly as I told you before, therefore I had in mind to rediscuss a little bit this case. It's similar in terms of injectivity. Here is full row rank 2. We can demonstrate also. We can demonstrate analytically. I do today now before closing. And another example. If I ask demonstrate it analytically, that this matrix is subject or represents the subjective transformation, like this. If I give you this transformation, this is the corresponding matrix. Why this is the corresponding matrix? I don't know if this is clear. It's the corresponding matrix because T of x, y, let me say so, is this matrix multiply the vector xy, exactly here. Let me explain this aspect as before. Let me do as before. Too large. This transformation, which is this one, can be expressed in this form here or using the matrix 6, 7, 2, 7, which multiply the vector xy. I don't know if it's, let me redo again because it's not clear in this representation. Now it's clear. Okay, let me go ahead. Yeah, basically, they say, oh, okay, this is nice. This is nice. This is nice. Look at this. We have this matrix here, which corresponds to a transformation between R2 to R3. Calculate the null of matrix A in order to discuss the injectivity, and then we will look about the surjectivity together. Before starting, nevertheless, with the calculation, so the exam, look at the vectors. What is the maximal rank here? The maximal rank is 1. Because, excuse me, it's 2. It's 2. The maximal rank is 2. The highest rank is 2, no? The number of columns, excuse me, the number of columns, top 2. No, cannot be more than 2. But it's really 2? No, it's 1. Because we have 2 equal, depending, or equal in particular, column. Oh, interesting. Interesting. We didn't see this before. Huh? We have seen something similar, but full column rank. And we have seen, as I told you, if full column rank, we have seen also in the presentation, we have in a transformation which is injective. Now it's not the case. This means probably that is not injective, in fact, but to demonstrate, I show you exactly with the calculation. But why it is not injective? Because if you remember the concept of the independence, if this two row is not is depending, if two row is columns, if two column is independent, of course I can generate zero not only with 0 0. You remember, if I do the linear combination of these two vectors, we say that these two vectors are independent if generate 0 0 just meet alpha 0 and beta 0. But we can see that this is not valid. We will have a combination, in this case alpha equal 1 and beta equal -1, we generate 0. This means, of course, the kernel is not just the element 0 0. This means a matrix which is not full column rank, as I told you before, is not injective. Look. I calculate now the element xy, or alpha beta, as I told you, alpha beta could be also xy. This is exactly the exercise which I presented at the beginning of the semester to generate 0 0 in the context of the kernel is everything in the concept of possible transformation. But if you think about what we did, linear combination of linear combination is exactly to judge if these two columns, columns are dependent or not. And then look, x plus y equals 0, 3x plus y equals 0, no, row multiply column equals 0, row multiply column equals 0, row multiply column. From here I have this one for each y. If I plug in here, I have a 0 0. If I plug in here, I have a 0 0 for each x and each y. I mean, this is 0 0 means is always valid. No? 0 0 always valid. No? Very important for each y. I mean, 0 0, I don't need to specify, no? But this is important if I write in this form. This means, as we did until now, I can characterize the kernel in this form -y 0 because I am considering as a free parameter y. You can consider also alpha beta, no? Instead of y, you have beta. But you can see that we have a dimension. It's not the element 0 0. This means the dimension is 1. It's not injective. This means if the rank column or the rank of the column is not full, we are not in an injective. Why that? Because we have a combination, a consistent combination, alpha, beta, x, y, we generate 0. It's not only 0 0. Now we will see how important what we did at the beginning of the semester. If I do the same exercise, considering three vectors, 1 0, 3 3, 2 2, we generate the element 0 0 0 0 0 0, I can demonstrate that the transformation is not surjective. I do this calculation and then we conclude. We did a lot today, even though just win one block. Next week, as I told you, I will start a little bit. I don't want to introduce the differential equations. We will go in depth on what we already did in order to prepare in the best way for the examination, if you agree. This means, as today, I will reconsider, we'll discuss, and I will upload many exercises in my study so you can redo, you can see the solutions of. Let me do the last exercise, which is let me write so quickly, is the following surjective. We know the answer. We know the answer. It's not subjective. Why that? Because it's not full. It's not full row rank. Because it's not full row rank. This implies not surjective. Let me do analytically. Analytically means this. You can write X, Y, Z instead of alpha, beta, gamma as you want. Gamma. Alpha plus 3 beta plus 2 gamma equals 0. Alpha plus 3 beta plus 2 gamma equals 0. Clearly, they are depending. And you remember the criterion. 3 vector into dimension. Remember one possible intuitive criterion. This means alpha equal minus 3 beta plus 2 gamma. If I plug in here, I have 0 equals 0. If I plug in here, I have a minus 3 beta plus 3 beta minus 3 gamma, 2 gamma plus 2 gamma. Look, what I can write here for each beta and gamma. For each beta and for each gamma. This means we have the rank 1, as I told you. What we can see from before. We have seen. You remember? The dimension of the kernel, here, yeah, the dimension, I forgot the kernel of, excuse me. Let me do. It's intuitive. I told you, but I forget to write. The dimension, telling about the dimension of the kernel is 1. This means the dimension of the domain is 2 minus 1. This means the dimension of the image is 1. The dimension of V minus dimension of the kernel, this is the domain, equals the dimension of the image. The dimension of the image, this means 2 minus 1 equal 1. The dimension of the image equals the row rank. It's equal 1. This means we have just one row independent. Because I can choose these 2 parameters. If you want, I can write a little bit more in depth, but we can see that let me say the level of independence, if you want, is 1. It's easy to see. 1, 1, 3, 3, 2, 2. This we can see that we have 2 free parameters. I can choose as I want beta and gamma, but of course, alpha must respect this. Now, let me conclude. The row, it doesn't matter if I write the row in form of column, depending. This imply image of A not equal dimension of codomain. This imply no surjective. Okay, why this topic is important? It's important because sometimes in physics, in modeling, we need to invert the transformation. Because if you think about the transformation represent a physical phenomenon in which we have some causes and some effects, but very often we have the effect. We perceive the effect. But if you're able to build a model, very often it's important to reconstruct which cause generate this effect. This means, first of all, we can say directly that to judge if the system is injective is extremely important, because if it's not injective, we have an effect, but we have more than one cause. This means we have to aware that when we say this is a possible cause, to emphasize possible, because it could be that we have another one, or both concur in this effect. And not only if the system of the transformation, the system in the model system is not surjective, also is strange. It is difficult to conclude really something, because we have some effects, but we don't have the cause. Or we are not able, with the model which we have, to recognize the cause. In both cases, we have to be careful. In terms of the subjectivity, is not so dramatic because we can reduce, but nevertheless, we have to be aware that why we have an effect and we are not able to localize mathematically in the sense of model and a possible cause. Probably it's the model which is wrong, probably, but could be also different aspect which is not completely clear in the physics, or more probably in the model. Yeah, we will see next week, but I will communicate exactly the schedule. We can do also this week. I am in the lab, excuse me for today, but I think a good choice to go ahead, remain a little bit. I close the lecture and then we'll discuss a little bit the organization. Thank you for attending this class. Excuse me for today, and remain, please. We discuss a little bit. Thank you.